Today we're going to go over a hodgepodge of information, starting with the distance and midpoint formulas. So given a segment and it has, say, endpoints of x1, y1, and x2, y2. If I want to find the distance of that, remember the distance formula came from basically constructing a right triangle and then using Pythagorean theorem. So the difference of x's squared plus the difference of y's squared. So here's x2 minus x1, and here's y2 minus y1, and here's d. So a squared plus b squared would equal c squared in theory, and then you square root the c squared side, and you end up with the distance formula. The midpoint is just halfway between these two x values and these two y values. So we take the average of the two. So if I wanted to find the distance between, let's say, let's go 2, 8 and 8, 9. So roughly somewhere like 2, 8, 8, 9-ish, something like that. Again, take the difference of the x's, so that's 8 minus 2, square it, take the difference of the y's, 9 minus 8, square it, square root that whole guy. We got 6 squared plus 1 squared is equal to, root is to 37, and I leave it as is. If I want to find the midpoint, so that distance, midpoint, take the average of the x coordinates, so that's 2 plus 8 over 2, and 8 plus 9 over 2, which gives me with 5 and 8.5. There's your distance and midpoint calculations. Next, we're going to talk about x and y intercepts, and if you remember, I don't care what your graph looks like. It could be a curvy looking thing like this, but regardless, any x-intercept, anything that hits the x-axis, is going to have within the point that it hits at some unknown x value and a y value of 0. And any y-intercept within its point will have some unknown y value, but its x value will always be 0. So if I want to find intercepts of the following functions, all I need to do is set x equal to 0 for the y-intercept and y equal to 0 for the x-intercept. So let's do that for each of these examples. X-intercept, y equals 0, 3x plus 2 times 0 is 16. So 3x, 16, and the x-intercept, 16 over 3. The y-intercept, so x equal to 0, so 3 times 0 plus 2y is equal to 16. 2y is equal to 16, and y equals 8. In the next example, I don't care what the function looks like, an x-intercept will have a y value of 0. So if I want to find the x-intercept, set the y equal to 0. Therefore, I have 17 over x minus 3 is equal to 0. So this brings up a special case because I need to solve for x, in which case I multiply x to both sides of the equation. In doing so, I have 17 then equals 0. Therefore, there's no solution or no x-intercept for that graph. For the y-intercept, I'm going to set x equal to 0. 17 over 0 minus 3 is equal to the y-intercept. So I have 17 over negative 3, and that is my y-intercept. Last function, let's take a look. Now in this case, we set for x, for the x-intercept, I'm going to set the y equal to 0. So what I have is x squared times the root of x plus 12 is equal to 0. Notice this is a product, so one of these two terms must equal 0. I have x squared equaling 0, and I have the root of x plus 12 equaling 0. Now, we solve each of these. Square root both sides, x ends up equaling 0. Square both sides of this equation, I have x plus 12, show the squaring, is equal to 0, so x equals negative 12. So there are two x-intercepts in this case. For the y-intercept, I just set x equal to 0, so I have 0 squared, root 0 plus 12 equals y. 0 times anything is 0. So that's my y-intercept. Next, we're going to talk a little bit about symmetries. I've got two types that we're going to look at today, point and a line symmetry. In a line symmetry, the line is the axis of symmetry if it's the perpendicular bisector between 2 points on the graph. So as you can see here, here's a line of symmetry. And if I take 2 points on a graph that are symmetric about a line, that line of symmetry is the perpendicular bisector between those 2 points. The point's point of symmetry if it's the midpoint of a segment joining 2 points. So in this case, here's point 1, point 2 on a graph, and I say those are symmetric over this point. Therefore, that segment has to have this point of symmetry as the midpoint of its segment. Likewise, if I were to take two other points, let's take this point right here and this point right here, and if I were to do my best to draw a straight line, which would be terrible, but there's a straight line, it appears that on that segment, that point is the bisector of the segment. So the type of line symmetries we're going to look at are basically two. We're going to look at x-axis symmetry. In other words, the function reflects over the x-axis onto itself. And y-axis symmetry, once again, where the function reflects onto itself over the y-axis. Now you'll notice the relationship between points in all of these. If I reflect over the x-axis, my x-coordinate will be the same, but my y-coordinate will be opposite. If I reflect over the y-axis, the y-coordinate remains the same, but the x is opposite. And now if I look at origin symmetry and how their points relate, this function is origin symmetry, and I reflect over this point right here on the origin, and it moves down to this point, and you'll notice that in this case, if I start out with some xy point, I have the opposite of x and y as its image point, or as its reflection. Now let's say we can't graph all these. We don't know how to graph all the functions yet. So if we wanted to test to see whether a equation referenced a function that was y-axis symmetric, x-axis symmetric, or origin symmetric, we could do a test on the points. So here are the points and the test that we're going to use. For the x-axis symmetry, as we already showed you, the reflections are as such, and if both these 2 points yield the same equation when substituting in, you'll know that the function is x-axis symmetric. Here is the point in its image when I have a y-axis symmetry, and if you plug these 2 points in for x and y and result in the same equation, then you'll have done a test for y-axis symmetry. And again, here's the point and its image for an origin symmetry. And if you were to plug these 2 points in for x and y in your equation, and you end up with the same result, then you have origin symmetry. Let's apply this to a couple of problems. So what we're going to do is we're going to see if this equation here carries origin symmetry with it. In other words, if the point xy and the point negative x, negative y yield the same equation, then that will be origin symmetric. The point xy is just this equation right here. So this is xy. Because substituting x in for x and y in for y, I get the same thing back. Now what I'm going to do is substitute in negative x and negative y and see what I get. So I have negative y equals negative 3 times, instead of x, I have negative x to the third plus 5 times negative x. And I want to yield the same equation that I started with in order to determine if they're origin symmetric. So what I'll do is I'll say negative y is equal to negative x cubed is negative x times negative 3 is positive 3x cubed. 5 times negative x is negative 5x. And now I want to get y to have a coefficient of positive 1 in front of it. So I'm going to divide everything by a negative. Y equals negative 3x cubed plus 5x. And I want to now compare this equation with the original. And I notice they're the exact same. Therefore, little triangle, therefore, we have origin symmetry. Now let's take a look at this function. Y equals x to the 6th. I want to determine origin symmetry again. So I'm going to pop the point negative x, negative y into this equation. Negative y for y and negative x for the x value. And then simplify the two sides. Negative x to the 6th power is x to the 6th. I want a positive y here, so I divide each side by negative 1. And you'll notice in this case that because I have a negative value in front of the x to the 6th, it doesn't yield the same two equations. Therefore, this is not origin symmetric. Let's see if we can determine which kind of line symmetry exists. Remember the tests for x-axis symmetry? We said x remains the same, y is the opposite. And for y-axis symmetry, we said y remains the same, but the x value is opposite. So let's do x-axis symmetry first. And I'm going to keep x the same, but make y the opposite. You'll notice that I have the opposite of y. If I were to multiply everything by a negative 1 just to check, I have negative x squared plus y is equal to negative 8. So this is not x-axis symmetric. We can check for y-axis symmetry once again. By moving from x to negative x, keeping y the same. And you'll notice negative x squared is x squared plus y equals 8. Comparing that with our original, we notice they're the same. Therefore, this is y-axis symmetric. Now we're going to talk a little bit about circles. If you remember from last year in geometry, hopefully you got the equation of a circle. And the equation of the circle, also stemmed from saying, well, I've got some point on the exterior of a circle, call it xy, and if I were to take and move straight down and straight over from any point, I would create a horizontal distance x and a vertical distance y. If I wanted to set a relationship between the horizontal distance, the vertical distance, and the radius of that, I have a right triangle. Thus, x squared plus y squared was equal to r squared. And that's what you should have learned last year. Now, if we were to take and translate this somewhere out in space, and I called my center some hk, the equation for the circle would read as follows. X minus h quantity squared plus y minus k quantity squared would be equal to r squared. So now what we're going to do is we're going to write the equation of a circle with the center at 4, 6 and having a radius of 12. So my h value is my horizontal shift. So the center has been moved 4 over. So 4 acts like my h, 6 acts like my k, and 12 is my r. So it's just basically plug and chug. I have x minus 4 quantity squared plus y minus 6 quantity squared is equal to 12 squared, or 144. And that is the equation of a circle. No need to FOIL all these out. So our last equation, or our last problem, asks us to write an equation of a circle with a diameter having endpoints at 5, 12 and negative 13, 2. So let's go ahead and do that. 5, 12, let's say that point is, let's call it right here. Call this 5, 12. And call this point over here negative 13, 2. And then I've got some random circle going around. Like so. And those 2 points happen to be the endpoints of the diameter. So in order to find the equation of this circle, I'm going to need to actually find the center first, and then determine the radius from there. So in order to find the center, I know the center is midway between the 2 points, or the 2 endpoints, so I can use a midpoint formula. So the center can be found by taking the midpoint, or 5 plus negative 13 over 2, and 12 plus 2 over 2. So in this case, I've got negative 7. That's my midpoint, which is also my center. Next, I need to find the length of the radius. So I'm going to take and use the distance formula to find that length. So I'll take 5 minus -4, square that, that's the difference of x's, 12 minus 7, square that, that's the difference of y's, and that's going to equal the distance, or the radius, of the circle. So in this case I have 9 squared plus 5 squared, or 81 plus 25, which is 106, is equal to r. And remember, for my equation of the circle, we want x minus h squared plus y minus k squared equals the radius squared. So if my radius is squared, I square the root of 106 and I get 106. I take x and subtract off the h value, or the horizontal translation. So -4 is my horizontal translation, 7 is my vertical translation, so that ends up being k, and I just plug it in. So x minus a -4 is +4, and y minus 7 is squared, and there's the equation of my circle. Alright, I'll give you the homework, or your sub will give you the homework for the day, and we'll go over this tomorrow.